we are talking about aramid reinforced composites. And by aramid, I mean pretty much Kevlar. And last week you all saw a material selection video which was comparing glass fiber reinforced composites with Kevlar reinforced composites along with carbon fiber reinforced composites. So we're still kind of talking about fiber reinforced composites here. And it occurred to me that we're kind of talking about stuff that not everyone may be familiar with. And so I'm going to talk a little bit about the chemistry, and then there are some supplementary videos I'll also post that are far more well produced than my videos that will also give you some background information pertaining to some of the chemistry involved in this. And it's always good to have a background. And if you guys have already seen this, again, it never hurts to kind of see some of this stuff again. And so what I'm going to talk about now is we're going to talk about Kevlar. And Kevlar finds its way into the composites world, if you will. So you can do kind of cool things like this. So I snatched this from this article, compositesworld.com. If you want to read the whole thing, here's the web address. And let me, oops, uncomfortable delay as I turn on my pen. This web page here, if you didn't see it, go ahead and take a look at it. And so we have, you can kind of do some cool things. So you're combining Kevlar with a carbon fiber composite laminate structures, and then you're basically using the Kevlar as a living hinge. And a living hinge is any hinge that doesn't have mechanical parts. And so this is basically living hinge. And if you go look at a door, like a regular door, like to your room or whatever, you'll see that that's a mechanical hinge. And so you kind of have these interlocking parts with, I believe it's called a cotter pin or a linch pin, kind of holding that hinge together. A living hinge is just a folding structure, and a lot of times I just use a piece of paper as an example, but we have some pretty good examples here. And the Kevlar is also incorporated into the laminate structure for impact resistance. And Kevlar is if you don't know this, it's very famous for use in bulletproof vests and body armor. And here it's kind of cool because they're incorporating the Kevlar with these carbon fiber epoxy sheets, and the hinge part allows you to form your plates into different shapes. And so we kind of have this kind of cool kind of origami looking structure here. This, you're using it to make body armor. So you've combined it with carbon fiber plates, and the fact that you have this living hinge lets it conform to your body. And this would be like your leg. And this, you kind of see structures like this on, let me try to find a better color. You see structures like this on orthopedics, not orthopedics, excuse me, prosthetics. And you want something soft around the hinge of your body, so the leg area, the back of the knee here. And then here, this is really just the living hinge, this one here. And I don't know where that popped up. So a hinge structure there. So we're talking about aramids here. So Kevlar. And what is, oops. So Kevlar is an aramid. Sorry, and I misspelled it. It's almost embarrassing. I probably misspell quite more than I realized. Well, an aramid. So an aramid is a polymer. It's a class of polymers, and Kevlar is one. Nomex is it's also Kevlar, but it's just a different brand. And so in polymers class, if you all have taken that class with me, I talk about polycarbonate sometimes, and there's different brands of polycarbonate. But this is an aramid. And let's get to through a little bit of chemistry before we kind of understand, so we can understand what an aramid is. And so basic hydrocarbons. We'll talk about basic hydrocarbons, and I'll also show you a supplemental video if my brain doesn't shut off before I get through this. So hydrocarbons generally have carbon and hydrogen. So a lot of things are this carbon-carbon bond is a big definer. And so carbon-carbon bond. So we could also have CH, C bonded with H. So if you have single bonds, and actually it's more associated with the carbon-carbon bond. So a single bond, that's an alkane. If you have a double bond, so double bond, that's an alkene. And we'll talk about this a little bit in more detail. So if you look at alkene, here's a common one. And alkenes are also olefins. And so when you hear polyolefin, it's really a polymerized alkene. And so if you polymerize this structure, you get polyethylene. So this polymerized is and then you kind of want to use this nomenclature to show that it's a repeat unit. And so this is polyethylene. And that's an alkene, also known as alkane, excuse me, also known as as an olefin. So polyolefins. When we have C6, H6 in the ring structure, if I can draw it, and if some of you have had me in polymers, you've seen my pain in drawing ring structures. So two things I struggle drawing: ring structures for organic chemistry, and cubes when we talk about crystallography. And it's doubly embarrassing when I use like a little graph like this, because I picked the graph on purpose to kind of help me draw, and I kind of forget it's there. And let's see if I've drawn this well, and I don't really think I have. And let me erase this to fix it so I can kind of make it. My apologies, y'all. All right, so when we have this, and I'll have a supplemental video on aromatics because it's a really cool video. Actually, I enjoy watching it, and if it's Crash Course Chemistry, if you've not seen that on YouTube, and there's two flavors. There's a Crash Course Organic Chemistry and just plain old Crash Course Chemistry. Both of the presenters are very, very enthusiastic people. It's really cool to kind of see. So C6H6 is it's an aromatic. And if you want it to bond with something, so aromatics, so smelly things is where we associate this. So we see a lot of ring structures like this in like coffee. Coffee is very, in fact, that's where it comes from. What else has it? Polystyrene. So let's look at polystyrene. If you've ever broken polystyrene, you smell it, and even a Lego. So if you break a Lego which has styrene in it, you'll smell the plastic. I don't know if you all have ever experienced that, but if you look at polystyrene now, it has this aromatic structure here. And a lot of times when we see this, we think of rigidity and strength. So in this case of polystyrene, here this is a pendant molecule. And if you have the opportunity, and in polymers class I tend to kind of go through a little bit more detailed examples of some of this stuff. But if you get like a milk jug, which is typically polyethylene, and you find polystyrene, which if you ever buy compact discs, usually the box that holds the disc is polystyrene. If you look at drinking cups and you look at the bottom and it says PS, that's polystyrene. It's much more rigid than polyethylene, and it's because of the presence of this pendant molecule, this aromatic pendant molecule. If you break polystyrene, if you like take a polystyrene cup and break it, you can smell it, and you're actually smelling the aromatics. If you want it to bond with something, right? So it's kind of understood that there's a carbon here. There's a carbon here. Let me make it a different color so it's a little more useful. So that's probably the wrong color to use. I'm sorry you're watching me struggle. We'll use rainbow here. There's a carbon. That's more purple, but that's all right. There's a carbon here at every junction, and there's also a hydrogen at every junction. Okay, so branching off of this 6 carbons, there's also a hydrogen kind of branching off. All right, so to make this pendant molecule stick to this carbon, we knocked off a hydrogen. And so this, in this case, it's actually C6H5. And when we have C6H5, that's an arene. All right, and so again, this is still, this is an alkane. Well, it's kind of a double structure, right? Because we have these double bonds here, in here, and originally this had 2. Okay, so this was an alkene, but then when you polymerize it, it becomes an alkane. So it's kind of interesting. And anywho, so now we have aromatics. We're seeing that we see some polyolefins. If we replace, I'm trying to do this from memory again. We can get polypropylene as well, and I believe it's a CH2 if you replace a hydrogen with a CH2. And this is polypropylene. And the reason I'm talking about polypropylene is it's another common polyolefin, but we also have an article that I've posted that you can see a Kevlar reinforced polypropylene matrix composite used for impact shielding as well. So instead of using epoxy, it is polypropylene matrix. Excuse me, lost my train of thought again. I apologize. Speaking of epoxy, I don't know why I keep erasing letters today. That's an oxygen-containing hydrocarbon, basically, and so here's a common structure. And so there's an H at the end of all these. And these H's, one of these can be knocked off and you can make a polymer chain, so you can actually polymerize it. So this is C2H4O, otherwise known, if you look up here, This was ethylene, or sorry, this was ethylene. And when you polymerize it, it's polyethylene. If you come down here, you see this. This is very similar, right? We have 2 carbons, 4 hydrogens, but now we've oxidized it, sort of, if you want to think of it in terms of oxidizing. I think we just added oxygen is probably the more profound or more correct way to explain this stuff. This is ethylene oxide. I spelled it wrong. I apologize. And so what you find is there's many flavors of epoxies, just like there's many flavors of urethanes, and there's many flavors of polyesters. Although most times when we think of polyester, we only think of PET, polyethylene terephthalate, which is used to make drinking bottles. It's also used to make shirts and clothing because you can draw it into really thin fibers. The next thing I want to kind of talk about is an amine. And again, this is a really quick overview. We're not going to go through all the organic chemistry I tend to go through in polymers. This is a much truncated version, but it's mostly to show you some of the chemistry and some of the molecular structure, if you will, behind the stuff we're talking about. And I don't think we've talked about epoxy matrices in this class. Didn't really talk about the organic chemistry-ness of epoxy. Here's an example. If you see this type of group in a molecule, that means it's an epoxy. When we talk about thermoplastic and thermosets in terms of polymers, well, first I'm getting ahead of myself. Let me talk about amines. And so an amine is a nitrogen. It's a nitrogen containing hydrocarbon. Sorry, I'm so random going back and forth, but hopefully there's some order to some of this. And logging into something else at the same time. An amine is a nitrogen containing hydrocarbon, and so when we have R here, this is it can mean an atom, but it can also mean hydrocarbon. So this could be a hydrocarbon, so this could be anything. It could also be an atom. X is halogenoise. It could be a hydrocarbon, hydrogen, or any atom. And so these are abbreviations for organic molecules when we draw it out. So now I'm going to draw an amine. And here I'll kind of color code. An amine, nitrogen containing hydrocarbon. And so if I do it this way, okay, this could be a hydrocarbon, hydrogen, any atom. So, you know, an amine is basically something bonded by a nitrogen. And if you look at, let me see, let's look at this kind of methylamine. And let me draw it out here. Boop, 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 doo, doo, doo. All right, so this is a methylamine, and it's that same structure, right? So we've replaced hydrogen, hydrogen, and then a CH3 on one of these R's. You see what I mean? So That's kind of the code. When you see an R in an organic molecule, they're really just truncating the structure and replacing a hydrocarbon group with something else. And so it helps to draw stuff out. And all right, so we've hopefully built a foundation for why we call Kevlar, or so we can explain why Kevlar is referred to as an aramid. And to do that, let's kind of draw the structure, and I'll do my best to draw the structure of Kevlar. And so we kind of have it's a polymer. Okay, so I'm going to draw the repeat unit. So we have this N hydrogen. So we know there's kind of an amine structure here, and I'm probably not drawing it 100% geometrically accurate because molecules have angles and stuff like that, but I'll do the best I can. So we have this aromatic group. We have the full-on amine group. And another aromatic group. And then here we have our, and I'll draw the carbon again because I drew it there. If you just have the point, it's understood that there's a carbon there, but I'll draw the carbon anyway. And that's the repeat unit. All right, so there's kind of some things here. And what the thing we want to talk about is this here is an amide group. And if you look at the repeat unit, I'll change the color here. Let's see, what's a good one? This pinky. There we go, it's pinky purpley. If you look here, this is half of the group, and this is the other half of the amide group. Do you see that? So we have this NH, which is this, and then we have this double bond oxygen on this side. So the linkage is the amide group. And so this is a polyamide. Polyamide. There's another one, polyimide. But let's look at another molecule to kind of, it's a little less confusing, I think, if you see it in terms of nylon. And so nylon is basically this structure. And we'll just kind of draw it like that, NH. And then I'll draw all the atom or the elements out here. I'll only do nylon 6 because it has 6 carbons. Oops, hold on, I messed up. 1, 2, 3, 4, 5. This one gets the oxygen. Excuse me. And again, all right, so here we see that we have half the amide group. So this is nylon 6,6 because there's 6 carbons on the chain, or nylon 6, excuse me. because there's 6 carbons in the repeat chain. And so this is also a polyamide. Again, the amide group is the linkage. So this again, to kind of see the difference, there's another flavor, and I have this errant mark there. Okay, so another flavor, we have polyamides. So this is different. This isn't what Kevlar or nylon is. An example of a polyamide is, I don't know if you guys have ever, if all have ever worked with this, but like Kapton. I used to do a lot of work with Kapton. And it's a polyamide film. And it's a pretty heat-resistant polymer. It was used on the Apollo space mission. And I used to use it as a substrate for conductive inks back in the day. And so Kapton, not all ring structures are arenes, and so this is a different type of ring structure. And it's bonded to an arene. So I'm drawing it the best I can. It's not the best rendition of Kapton, but you can, if you really want to see a pretty picture, there's plenty all over the place on the web and whatnot. This has a nitrogen bonded there. And so we're starting to see kind of some familiar architecture in the molecule, if you will. And I really hate drawing these. I should have just cut and paste a picture for something, but anyway. So sorry, I did not, but hopefully this is adequate enough to give you guys give you all a idea of what the difference is. So this is the repeat unit of the polyamide. The difference here is that you still have amide groups. Okay, so there's hydrogens in here as well, and so you still have amide groups. So there's a hydrogen somewhere here too. So hold on, let me kind of decode by looking at the amide group. So there's a carbon going with an oxygen, there's a nitrogen here, and there has to be a hydrogen linked somewhere. But anyway, going to the other carbon. So I'm trying to identify the actual amide group, and I think it's probably this. It's in there. I might be cutting part of it off, but there's amide groups in here, and this is also a nitrogen here, but it's not providing the linkage. Okay. Let me kind of redraw it. All right. Hopefully I didn't make this more confusing than it needed to be with my kind of bad drawing. But here we have amide groups also. But these amide groups are not responsible for the linkage, and it kind of looks like it is, but the key thing to remember is that we haven't cut it in half. Okay, so here the whole amide group is in here. Okay. And so it's not being cut in half, basically. That's how I think of it. So nylon, we've cut the amide group in half. The amide group is responsible for the linkage. Kevlar, we've cut the amide group in half. It's responsible for the linkage. Here we've not cut the amide group in half. So there's an amide group on the end, but it's not responsible for the linkage with the next repeat unit of the Kapton. And so this is a polyamide. Okay, so that's the difference between polyamide and polyamide. we care about polyamides here simply because we're talking about Kevlar. And Kevlar, it's an aramid. And so Kevlar is a polyamide. Excuse me. Here, let me draw it in a different color to give the punchline. And it also has aromatics in it. So it's called an aromatic amide, or just aramid for short. And so that's why it's an aramid. So a little bit of organic chemistry background. You'll have some kind of supplementary documents, or not documents, videos to watch to kind of reinforce this. Apologize if this was a little choppy. I'm drawing, and in the future maybe I'll actually just put pictures, but sometimes it helps to watch me draw out the molecule so you pay a little bit more attention to the structure. And so hopefully this was helpful to you guys. And if you all ever have any questions, feel free to email me.
Oh my.
It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.